Okay, this time we are going to talk about superposition of waves and stationary waves. Here are some examples of some standing waves. And we can have different forms depending on how the ends of the wave look like. Are they closed end or are they an open end? Well, let's look at the concept of standing wave. We need to understand the concept of the harmonics. And we're going to understand how standing waves can be used to establish the frequency of a set of waves. Well, we know that when a wave is traveling, a pulse is sent down a string. We can see how two waves interact through interference. This can be either constructively or destructively. So yes, wave can actually construct each other or deconstruct each other. So you can actually make a louder sound with sound, and you can actually silence sound with sound. The same happens also for light. All behavior of all different types of waves. Now, a stationary wave or a standing wave is formed when two waves pass through each other. Okay? So, for example, we have a string on one side, and at the end we have a closed end, and we are going to give the string some vibrations. At the end, on the other side, the wave will bounce back, and then of course the movement of the initial wave is still going on, and depending on the frequency we will get different types of standing waves. So the reflected wave will interact with the wave that is coming, and they meet and interfere. Okay, let's see what is going to happen when we have a wave going to the right, and now we are going to use a fixed end. And let's see what is going to happen. I'm going to let it oscillate, and what we see is we get a standing wave almost, and we can change a little bit the frequency. And it's interesting to see, especially the green dots almost at the end. You see they hardly move, and we have maximum displacement. Let's lower the frequency even a little bit more. Standing wave, we don't want to have damping. This is a clear standing wave. Now what do we see here? If we look good, it's a little bit vibrating, but we see that there are points on the waves hardly moving, and wherein we get maximum movement. More or less the same will happen with an open end, only the pattern will be a little bit different, which we will discuss later. Okay, now let's look what is happening here. We have one wave coming from the left and one wave coming from the right. Now that means two waves. Now where we have maximum amplitude, we get a resultant disturbance almost, or probably mostly, a double amplitude. When we go to B, wherein actually the waves are having the opposite motion, then we see that actually the waves are completely destroyed. Yeah, depending on the phase difference, we will see whether it's a complete destruction or a complete construction. So, in one, they are in phase and the waves reinforce each other. In two, a half wavelength ladder, each has moved a half of a wave the opposite directions, and now the waves are in anti-phase. That means they are cancelling each other out. Yeah. And again, a 1/4 of a wavelength later, the waves are again in phase, and this time the resultant is larger than the wave in the opposite direction. So it's like the waves get a superposition. That means the particles now are moving, but there are also particles that are not moving. Let's look a little bit at the phase difference. Not going too deep into that. The superposition actually means that there is a combination of the waves and that there is interference between the two waves. In this case, we have antiphase. Antiphase is wherein we get complete destruction. Okay? So, in phase, meaning exactly the same, we get addition, antiphase, cancellation. Okay? Now, the overall effect depends, of course, on the relative amplitude and the frequency and the phase difference between the waves when they meet. And this is what we call superposition. So, when a crest meets a crest, we get a supercrest, and they are thought to be in phase. When a crest meets a throw, we get cancellation, and they are out of phase. And this is all, again, what we call constructive and destructive interference. Some things to understand: where there is no displacement, that's what we call the nodes. This is the node and this is the node. So at these points there is no movement of the particle on the string. Then we have the antinodes. They are here and they get maximum displacement. Okay, antinode, maximum displacement. Everything that is in between has a different amplitude. So think about how is this movement going. Here we have no movement, and let's say this one is tending to go down, so we get this movement up and down, up and down, and this one down, up, down, up, down, up, down, up, yeah, etc. Now, how does this look when we are going to make use of music instruments? We are talking about harmonics, okay? This is the simplest standing wave considered of a single loop with a note at each fixed end. So we have N and one antinode. So here we have a note and a note there. So this is the frequency. The first one, we call that the first harmonic. The second one, when we increase the frequency, we get a second harmonic. And the third one, we get the third harmonic. The first one, we call it the fundamental modes, or the fundamental frequency. Okay. No, when this is occurring is when there's a distance of half lambda. Now think about one complete wave is like this. Okay, one complete wave. Now we see that this is half of the wave. I didn't draw this correctly, but try to do it better. This is one wave starting from the middle and there. Okay, this is one wave. Okay, so this is half lambda, and that is for the fundamental. Okay, okay, this is the second when you increase the frequency. Now let's look how is that of standing waves in different instruments, and we're going to discuss some instruments with different types of ends. Okay, you know what is this? This is a organ they use in churches. Fundamental and order frequency. Two close ends. That means if we know the length, the length is then equal to half lambda, as I explained in the slide before. This is for two ends. Instruments when we use that, a guitar. In the second one, we see that L is equal to lambda in the second overtone. In the third one, we see that L is 1.5 lambda, and in the fourth one, L is 2 lambda. Yeah, used in guitars and pianos. Here we have something else. We have one closed end, and we have an open end. There, right. So, what would be the length? What would be the length? What would be the length expressed in lambda? Now think about what is one complete wave. One complete wave is this. So how much part of a wave is that? The first one is 1/4 of a lambda. Now the second one is 3/4 of a lambda. And the last one is 1 and 1/4 lambda. This is for one closed end. For example, clarinet and trumpet. Okay. So when the valve is moving, it's going to detect points where there's a louder sound. That is where we have the anti-notes, and where it's almost completely silent, we have the notes. Okay. And this is at a standard frequency. Okay, let's have a look a little bit further. Well, you get the idea a little bit. Okay, this slide we have an instrument where there are two open ends. Again, we can find the lambda compared with the L. In this case, we have L is half lambda. In the first one, first harmonic, the second harmonic, F2 is 1 lambda. And the third one, F is 1.5 lambda, and then F is 2 lambda. Okay, so this is about superposition and harmonics. Okay, examples of this is an organ that you will see in the church. Yeah, here again all the fundamentals and the order of the frequencies. Oh, it's working. Yeah. Oh, okay. It's working. What do we see? We get bending. Again, close and look at that. We get more rounding. Okay. Now, what will happen if we have two slits? And that's interesting. And let's close the slit width. Now, this is interesting. What we see behind is that we get like an interference between the waves. Yes, I hope you can see that. Okay, so this is actually the two slit experiment. We can also use two waves. And now we have two sources of waves, and again we get, you see that grayish line here, the grayish line we get here, there's like destruction, there's like destruction, and here we get construction. Yeah, and we're going to talk about that. How is that working with light, right? In this slide, we're going to look at the interference of two sources. How do we make two sources? What are the conditions? And what is going to happen, and which formula do we have to use? As I showed you in the previous slide, we saw interference pattern when a wave hits two barriers, two openings, and behind the openings you will see like there's a part where we get destruction and there's a part we get construction. So, we're going to understand the double slit interference experiment, the use and implications of the experiment. We will be able to complete calculations which we call the Young's double slit experiment. Yeah. Alright. Now, in this case, we're going to use light. You could use laser light, you could even use white light, but the best way is to use laser light with one frequency, as you have seen already when we did one of those labs. Okay, we need two coherent sets of waves. Yeah, and we need a screen wherein we can see the interference pattern. Yeah. So in order to reach this, you have a source, one opening, then exactly in the middle you have two openings. That means that they on the second screen they arrive at the same way, and then we have a third screen wherein we are going to investigate the interference pattern. And this is what we call Young's fringes. Okay. So we're going to look what is the effect when we change the fringe separation. What is the effect when we change the distance between the screen and the slits? We're going to check the wavelength of light. We're going to look at the slit separation and how are they related. Okay, I've shown this already. Okay, the derivation. Don't worry, you don't need to really exactly understand the derivation. However, you need to understand the principle and why we get interference. Remember, we talked about the superposition of the waves when they are in phase and when they are out of phase. Okay. The fringes are observed at point P from light source 1 and light source 2. Now you see there is a path of difference, yeah? Okay. They are emitted at the same time, however, S1 is traveling a longer distance than S2. Because of this path difference, we get S1P minus S2P. And what we want when we have constructive interference, and the P waves then must be in phase, so SP1 minus S2P is M times X, wherein M is a normal number. In phase. For destructive waves, the waves must be at 180 degrees out of phase, so S1P minus S2P is M plus a half lambda, wherein M is again normal number. Okay, you may check this, don't need to derivate, but we need to understand the formula for the double slit experiment. Okay, we have the lambda, we have the fringe, we have the distance. Okay, so for the Young's modulus we use this formula. Okay, lambda is the wavelength, X is the fringe spacing, the spacing between the fringes, A is the distance between the slits, remember where the light goes through, and D is the distance from slits to the screen. So where we have construction, sine angle is M times lambda over D. Okay, and when we have dark fringes, we have M plus half times lambda over D. Okay, and I want to show you how we get these fringes in another application.